In this video, we're going to talk about a data structure called a linked list. I would say that linked lists have somewhat fallen out of favor for use in practice on modern computers. But they're still a fundamental data structure, and it is very important to know what they are capable of and what their limitations are. Knowing how to implement a linked list is also a prerequisite for building more advanced data structures like binary search trees that we're going to cover later in this course. Okay, so let's get into a linked list. A linked list is like a resizable array. It's a sequence container, which means that we store the elements in a linear way. The advantage over a resizable array is that in a linked list, it is fast to insert and remove items at both the front and the back of the list. The disadvantage with a linked list is that we give up random access to elements. To set or get the ith element of a linked list, we just have to iterate through the list, starting from the beginning or starting from the end. So there's a subtle point about linked lists, and that is around inserting or removing an element from the middle of a linked list. We can locally insert or remove an item from the middle of a linked list without having to shift the elements around it in memory. So this makes it fast to insert or remove an element from the middle of a linked list. Again, this is an advantage of a linked list over a vector. Now you're saying, but wait, how can it be fast to insert or remove in the middle when I just said that it's slow even to access the middle of a linked list? So the catch is that to quickly insert or remove an item from the middle of a linked list, we need an extra piece of information. And to describe this piece of information, we need to know something more about the implementation of a linked list. So this time, I'm going to start with the implementation of a linked list. So start about the data structure itself. And then only at the end will I go over the abstract data type that data structure implements. Okay, so remember that in our implementation of a resizable array, values were stored contiguously in memory. In the implementation of a linked list, this is not necessarily the case. Values can be spread out in memory. So this immediately solves the hassle we had in a resizable array of allocating a new array when our current one got full and copying all the elements over. When we add new elements to a linked list, we don't have to change the memory locations of the existing elements. But we do have a new issue. We need a way to link together all these values spread out in memory. That's the origin of the name, linked list. Now the basic unit in a linked list is a node. A node is going to contain two pieces of information. It's going to contain a data value and the address of the next node in the list. Having the address of the next node in the list is how we're going to link up the nodes. So here we're representing nodes as taking up two words of memory, one word for the data value and one word for the address of the next node. So here's an example. Let's say we have a linked list with the values 5, 8, 10, and 11. I'm sorry, 5, 8, 0, and 11. The nodes containing these values can be anywhere in memory. So you see that the node with the first value, 5, is at address 5 in our memory. The addresses are given by the tiny blue letters underneath the cells. In the second word, this node contains the number 12. So 12 is the address of the next node in the linked list. So if we go and look at address 12, we see that the data value there is 8. And 8 is the next item in our list, if you look at the array version of the list above. The address in the second word of this node, the node holding the value 8, is 2. So then we can go and look at address 2, and there we find the data value 0, which is the next value in our list. And then we look at the second word of this node. It has the number 17. So 17 is the address of the next node in the list. When we go and look at address 17, we see the value 11. The second word of the last node also has an address of memory. And you see that I'm using this funny symbol here, the null point, the empty set symbol. And that represents a null pointer. So this empty set, it basically is just an invalid address. It's an address which doesn't exist. Okay, and we call that a null pointer. So all that does is just indicates that there are no more nodes in the list, right? Since this is an invalid location of memory, a memory location that doesn't exist, that tells us that there are no more nodes in our list. We have reached the end of the line. So a linked list also needs to store the address of the first node in the list so that it can find where the list starts. So usually this is stored in a variable called head, which is a pointer to the first node in the list. That is, it has the address of the first node in the list. So the value of head in this case would be 5. That's the address of the first node in our list. So I wanted to show you the memory picture of a linked list to emphasize that nodes can be spread out in memory, and they're not necessarily in any kind of order. From now on, however, I will usually draw a linked list like in this picture, which makes it easy to see the sequence of values. Also, instead of writing memory addresses, I'm just going to draw arrows that point to the node whose address is stored in the second word. So this makes the sequence of values clear. To be more concrete, I'm going to go over some code for the operations on a linked list in C++. So here's the specification of a node. We have a struct called node, and it has 2 member variables. The first one is just an integer called val, and the second one is a pointer to a node. And this is going to hold the address of the next node in the list. And I'm just initializing val to be 0 just to give it some default value, and I'm initializing next to be null pointer. And you can find all the code that I'm going to discuss in the next few slides at this Godbolt link. Okay, so let's create a simple linked list by hand to hold the values 1, 2, 3, 4 in that order. The first thing that I'm going to do is just to create 4 nodes called 1, 2, 3, called first, second, third, and fourth. And those are going to hold the values 1, 2, 3, and 4 respectively. So I'm initializing the nodes here with what's called Aggregate Initialization. I can use this because node is a struct, so the member variables are public, and there are, in my node here, there are no user-defined constructors. So in this case, I can just provide a list of values, and these values will be used to initialize the member variables in the order in which the member variables are declared. So you see in this case, for each of first, second, third, and fourth, I just give a list with a single value. This value is going to be used to initialize the first member variable, which is val. And since the second value is not given, the next value is just going to take on its default value, which is null pointer. So right now, my nodes look as in the picture here. So I've created 4 nodes. The integers they store are 1, 2, 3, and 4. And the next member variable is null pointer in all 4 cases. You can read more about aggregate initialization from this link to the Learn CPP website. There's something to watch out for when you're using aggregate initialization. Since the values in the list are used to initialize member variables in the order in which the member variables are declared, if this order is later changed, or if a new member variable is added and put first in the struct, then this is going to mess up your code. So for this reason, it's always best to add new member variables at the bottom. For example, if I change the definition of node to also have a previous pointer, and I put this previous pointer first in the struct, then my code would no longer compile. So you would get an error here, which says invalid conversion from int to node star, because the compiler is trying to interpret the number 1 as a pointer to a node, and it can't do it. I just wanted to quickly mention that in C++ 20, a feature has been added to deal with this problem. So now we can actually specify which variable each item in the initialization list refers to. So you see I've done that with this .val here. The variables still must follow in the declaration order, but now we can have gaps, or we can leave some variables out. So now if I declared another variable before val in my node struct, like I did in the previous slide where I had this previous pointer, my code would still compile. Okay, so that was a little bit of a digression about C++. Let's get back to linked list. So now I've created my nodes with the proper values, and we still need to link these nodes up. So I can do that with the code snippet here in the top left. I just set first.next to be the address of second, second.next to be the address of third, and third.next to be the address of fourth. I don't need to update fourth.next because that was initialized to the default value of null pointer, and that's what we want. So here's how you can iterate through a linked list. So this is a standard idiom, which is just like, when you have a vector saying for I equals 0, I less than size, plus I. This is the same kind of thing. This can just be like automatic code that you can type out. So in our for loop, we declare a node pointer. I'm calling it current here. We set it to be equal to the head that is pointing at the first node. And we keep going until current becomes the null pointer. That tells us that we've reached the end of the list. And we update current by setting it to be equal to current pointing to next. So this arrow notation here, it's just some syntactic sugar. It's equivalent to dereferencing current and getting the next variable of that node. Okay, so you can try this code out. Hopefully it's straightforward how this works. Okay, now let's look at push front, adding a new node to the front of the list. So first we create a new node, which I'm calling 0 here. And I'm initializing it with the value 0 and next equal to head. So now this line of code sets us up with the picture we have here. So we have this new node with value 0, and it's pointing to the same node that head is pointing to. So there's just one more thing that we have to do to finish push front. So what is that? Well, we just have to update the head pointer. So now we set the head to point to this 0 node. So we just said head is equal to the address of 0. So you see that this whole process just takes constant time, right? We just have to update a couple pointers, and that's it. So push front is a constant time operation here. Yes, there's the update. We've updated the head pointer, and now we have a proper linked list. Now let's think about push back. Say that we want to add a node with value 5 to the end of this list. How long would this take? Well, the main problem here is that we don't know the address of the last node. So to find the last node, we have to start at head and walk all the way down the list. And that's a slow operation, right? That takes time proportional to the number of items in the list. We can easily fix this, though, by adding another pointer called tail to our implementation of the linked list. With such a pointer to the last node in the list, then we can also do pushback in constant time. First, we create a new node called fifth with value 5, and its next pointer being the null pointer. Then we say that the next pointer of the original last node should point to our fifth node. So we've updated as in the picture here. And finally, we update the tail pointer. So tail pointer should point to this new last node. So tail should be equal to the address of the fifth node. So again, now, given this pointer to the last node in the list, this whole process takes constant time. It's just done by these 3 operations here that are given in the code here. Okay, how about if we wanted to insert a node in the middle of the list? This is again easy if we're given a pointer to the node before the position where we want to insert the new node. So as an example, say that we want to insert a new node with value -1 in between the second and third nodes, and say that we're given a pointer to the second node, so this variable called pointer to 2 here. Okay, then what can I do? I can create a new node called 2.5, whose next pointer is equal to the address of the third node. And the address of the third node is just pointer to 2 pointing to next. So now we're in the state of the picture here. And to complete the procedure, we just have to update pointer to 2 pointing to next to be equal to the address of our new node. So that's this line of code. Pointer to 2 pointing to next is equal to the address of 2.5. So now we have successfully inserted a new node between the second and third nodes in constant time. Now suppose that we want to do the same thing, insert a node between the second and third nodes, but this time we're given a pointer to the third node instead of the second node. You see that now we're stuck. We have no way to access the second node, and we need to access the second node in order to update its next pointer. I should say we have no way to access the second node apart from just starting at the beginning and walking to it. So we have no fast way to access the second node. We can fix this problem with what's called a doubly linked list. So we just update our struct so that each node has both a next pointer and a previous pointer. And the picture looks like this. So now I've put the data value in the middle, and the box on the right is the next pointer, and the box to the left of the integer is the previous pointer. So here's what our struct looks like now. And we also have pointers to the head and the tail of the list. And note that the previous pointer of the node at the head of the list is the null pointer, and the next pointer of the node at the end of the list is also the null pointer. So in a doubly linked list, you can iterate through it forwards or backwards. So here's how we could iterate backwards through the list. So for a pointer to a node called current, we initialize it to be the tail. While it's not the null pointer, we just update current equals current pointing to previous. And now we're going to walk backwards through the list. So now, given a pointer to node 3, we can insert a node before it. We initialize our new node with in this case, we're initializing with the value 1. The next pointer is equal to pointer to 3, and the previous pointer is equal to pointer to 3 pointing to previous. So this takes us to this situation. Now we need to update the next pointer of the second node and the previous pointer of the third node. So we can do this as follows. Pointer to 3 pointing to previous points to the second node. So we update the next variable of this node to hold the address of our new node. So this gives us a way to access the next field of the second node, because that's pointer to 3 pointing to previous is the second node. So now we have the picture like this. And finally, we update the previous variable of the third node to point to our new node called 2.5. So now we've successfully updated our list. And again, this whole procedure, we just have to update constant number of pointers, so it takes constant time. Now that we know something about how linked lists are implemented, let's go over the abstract data type for a singly linked list. I'm going to follow the abstract data type for a singly linked list that's in the C++ standard library. In the C++ standard library, there's an implementation of a singly linked list that's called forward list. You can add an element to the front of the list and remove the first element of the list. So with the operations push front or pop front. And given the address of a node, you can insert a node after that node or remove the node after that node. Those are the operations insert after and erase after. So insert after and erase after I find a little bit subtle, as they're not completely abstract, but refer to the implementation of a linked list, and that it has this parameter, which is the address of a node. So that's why I wanted to discuss the implementation of a linked list before going over the abstract data type. And all of these operations can be implemented in constant time. So note that there was no pushback or popback in our singly linked list abstract data type. And I did it this way because that's how C++ does it in the implementation of a forward list. The C++ forward list is a bare bones singly linked list that's meant to be as minimal as possible. So not having pushback or popback means that no tail variable needs to be stored. There's also no size member function in the C++ forward list, saving having to have a member variable storing the number of elements. So this is really a bare bones implementation of a singly linked list. Here's an abstract data type for a doubly linked list, again modeled after the doubly implementation of doubly linked list in the C++ standard library. So now we can add or remove elements to the front or the back of the list. With insert, given the address of any node in the list, we can insert a node with a specified value before that node. And again, all these operations take constant time in the worst case.